There we go.
All right. Welcome, everyone. We are your tutors, Joe and Suleiman, and this is midterm one for CS220, discrete structures. I just want to say I understand that 220 is often considered one of the more difficult 200 level courses in the CS major. There's a lot of proofs, there's a lot of math, there's a lot of thinking in ways that you don't normally think when you're just coding. So I understand where some of the frustration comes from, but I just want to say don't be intimidated by it. We're going to take everything step by step. We're going to build it up. And just the fact that you're here on a Saturday preparing for your exam puts you a step ahead, and just be confident in yourself. We're going to get this. All right. So I just like starting with a little comic here. Um, can anyone say what they think is going on in this? Just as a little brief like coding thing before we do our CS 220. Can everyone hear me? Is my mic not working?
Yeah, it's working. They're all saying
Okay.
yes in the chat.
Oh, they are answering in the chat. All right. Yeah, let me check the chat. Cool.
Also, for those who are filling out the TIMS form, it has the option for 220. Um, yeah, so if you want to fill it out again, feel free.
Cool. All right. Yeah, we got the chat. All right. So I'm going to continue with the 220 material. This is really just saying this bool is setting false to begin with, and then the condition is equaling true, which means it sets the condition to true, and then it runs kill humans. This is just a little um, code, a little comic that sometimes might appear as a you know extra credit kind of quiz or something in other classes. But anyway, so I would like to start with, I see that you have, by Professor Delaram, we have the 12 cents that can be formed using 4 and 5 cent stamps, and every integer greater than or equal to 12 can be formed using these. This is a strong induction proof.
Yo, real quick, are you sharing your screen?
Not yet.
Got it,
I'm,
got it.
yeah, yeah. Just one second. So I'm going to share just a blank page, and then we can write on this and everything. So let me find it. Here we go. All right. Yeah. So our proof is that we want to show that starting with the number 12 and going up in integers from there, we can represent any integer greater than or equal to 12 using 4 cent and 5 cent stamps. So this is saying, actually, let's start with why 12? Like, why are we saying 12 to begin with? Well, let's see. Do I have, let me just make this blue. Let me make, okay, that's good. Okay, so we can say 1, 2, and 3 are impossible with 4 and 5 cent stamps. 4 and 5, okay, that's a single stamp. 6 is not possible, 7 is not possible, 8 and 9 are, 10 is, 11 is not. So 12 is the first one we're going to say that we can make using 4 and 5 cent stamps. This would be 3, oops, sorry, having little problems here. This would be 3 4 cent stamps. Sorry. God, I hate doing this. I'm just going to type it. Three times 4 cent stamps, right? Then we can do, actually, let's represent that with 4 plus 4 plus 4. Now, how would we get 12? This is called the basis, right? We're using this to kind of explain if we can do it this way, then maybe we can, extend it further using induction. So we're going to say that 12 is 4 plus 4 plus 4. So far, so good. 13 would be 4 plus 4 plus 5. We can only use 4 or 5 cent stamps, right? So we're just replacing one of those 4s with a 5. 14 is the same, right? We have 4 plus 5 plus 5. And then 15 is going to be 5 plus 5 plus 5. So we've proven so far that 12, 13, 14, and 15 can all be represented in some combination of 4 or 5 or both. So if we want to prove this using strong induction, anytime we're using strong induction, we're going to look at this as kind of like a range of some constant a less than or equal to some j less than or equal to some k. And if k is arbitrary and a we define, in this case we define it as 12, right? So we're saying 12 is less than or equal to j is less than or equal to k. For some k, this is going to be true, which means that for everything in between 12 and k is also true. That's j, right? So all we have to prove is that if k is arbitrary, and I can prove that this is true also, not only for this, but for k plus 1, then because k is arbitrary, k plus 1 is also arbitrary, and this kind of, you know that image of dominoes where you flick one down and then the entire thing follows? We're saying that our assumption from this range of 12 to 15 also asserts that 16 is true, which means that 12 to 16 is true, which also asserts that 17 is true, right? So we're just extending the range through what's called strong induction. So how to do that? If we say that k is equal to 15, we'll just do that here. I'll just extend this a little bit. Sorry, figure this out. All right, we'll just do this. For k is equal to 15, then we know that, let me do it here, 12 is less than or equal to j less than or equal to 15. Now let's say let me just make sure that I'm organizing my thoughts here. Yeah, so let's say that 15, if we want to represent that as, again, what we said that is k, let's have k equal to, let's say if k is 15, then I can say k minus 3 is greater than or equal to 12. And we see how that works, right? Because k can be bigger than 15. For k greater than or equal to 15, I guess I should say that, right? So if k is greater than or equal to 15, then k minus 3 is at least equal to 12, but could be bigger than 12 as well. Then we want to say, let's see, how are we going to take the next step? K minus 3 is greater than or equal to 12. Then we want to find, we're trying to prove k plus 1, right? So what's a way that we can rearrange this so that it looks like k plus 1? Well, we'll just say that 12 is less than or equal to, let's do k plus 1 minus 4. Or, all right, k plus 1 minus 4, k minus 3. Okay, sorry, I'm just trying to find my notes over here. I just want to make sure that I'm doing this right. So we know that k minus 3 is representable because that's greater than or equal to 12. So sorry, I think I just lost my place. Okay, I'm just going to
What are you lost in, Joe?
yeah, wait, I'm just lost on the step that we have to induce, right? Because we have k plus 1 minus 4.
Mm-hmm.
And if we say that that is equal to k minus 3, and we know that k minus 3 fits in with the induction because it's greater than or equal to 12, and that's in the range that we know is already proven to be true, then this minus 4 can be represented by a single 4-cent stamp. So if that's true, then all of these k plus 1s must also be true because this is equivalent to this k minus 3. Does that sound right, Suleiman?
Run it by me one more time. Sorry, I'm not. So J, 12 is less than or equal to J, less than or equal to K. K is greater
Hmm.
than 15. We're trying to prove that.
We've got 12 is less than or equal to k minus 3, and the reason that we're saying that is because k itself is 15. So k minus 3 still fits in the range of greater than or equal to 12. Because does that make sense?
Well, okay. What I was thinking is now we know that this is our range so far, so we could say that for any n greater than, say, like greater than or equal to 15, right? That it could n equals 4k plus 5l. And then we want to prove that n plus 1 is also equal to the form 4k plus 5l. Um, well, what do we know here? We know that because n is greater than or equal to 15, n minus 3 is also equal to the form of 4k plus 5l, right?
Mm-hmm.
And then because n minus 3 is going to be within the range here because n is greater than or equal to 15 and n minus 3, 15 minus 3 is 12, which we know is good.
Yeah.
So that means n minus 3 is equal to 4k plus 5l. But I
Right.
want to get n plus 1. So what I'm going to do is I'm going to add both sides plus 4. Minus, sorry, this is minus 3. Minus 3 plus 4. Bless you.
Thank you.
4k plus 5l plus 4. Right? N minus 3 plus 4 is n plus 1. I'm going to bring the 4s on one side. So this is going to be 4k plus 4 plus 5l. I'm going to factor out the 4, and I'm going to get 4 times k plus 1 plus 5l is equal to n plus 1. What do we want to prove? We want to prove that n plus 1 is equal to 4 times something plus 5 times something. Let's let m, not m is a bad number, bad letter here. Let's let j equal to k plus 1. Lo and behold, what do we get? We got n plus 1 is equal to 4j plus 5l. And we're done.
Okay. All right. That was the step that I was missing.
Yeah.
Thank you. Okay. Yeah. So again, we're just trying to prove if we have everything that's proven within a range, and then we extend that range by what we're doing here with the n plus 1, and everything is still working, then we can say that for any arbitrarily large number, everything in between is also going to be proven. So,
Anissa's asking, what does L represent?
okay, so we have 4k plus 5l. That's just an algebraic way of saying some number of 4 cents plus some number of 5 cents. So the k and the l, you can think of the number of stamps, right? So some number n is represented by 4-cent stamps, a certain number of them, k number of 4-cent stamps, plus um, an l number of 5-cent stamps is going to equal n, right? So when we solve this for n plus 1, we're ending up with some other constant, but it's still a constant that is multiplied by 4. So you have 4-cent stamps times j, and j over here is n plus 1, and 5-cent stamps times l over here. And that will still be some number of 4-cent stamps plus some number of 5-cent stamps. And if you want to convince yourself further, you can look back at this example of replace all the 4s with 5s. That gets us up to 15. Then to get up to 16, we can just say that 16 is 4 plus 4 plus 4 plus 4. So now we have all 4s again. Then for each of those, we can replace the 4 with a 5. So that would make us have 17, 18, 19, and 20. And now we have 4 5s, right? But 20 can be represented by a group of 4s again. We have 5 4s. Each of those 4s can be replaced by a 5 to increment up by one number each time. And what we're really doing is we're just trading off fours and fives. So logically, that's what's happening. This is just the algebra that supports that.
I will say one note. It's important the number of base cases you have, especially when it comes to strong induction. Because see here, we were able to use the implication that n minus 3 is equal to 4k plus 5l because our n is greater than or equal to 15. If I were to use, and here it works out because I'm adding 4 on both sides. But if I wanted to do something with the 5 cent stamps, then I would have to prove 12, 13, 14. I would have to explicitly write out 16 and a set n greater than or equal to 16. Because then otherwise I'm gonna have to I would get a implication that that isn't necessarily true. So it's important like you have the number of base cases written out. So
Hmm.
yeah.
Okay, yeah. All right, cool. So I can't really see. Okay, so do we have any more questions in the comments? There we go. Oh, the n minus 3. That was, well, we have n plus 4 and, no, n plus 1 rather, I'm sorry. And if we subtract 4 from that, it's like taking away a 4-cent stamp, right? So if we end up with n minus 3, it's the same as n plus 1 minus 4. And that's kind of what I tried to show earlier in that example. But Suleiman, does that sound right? Am I explaining that correctly? Where we're getting the n minus 3 from?
Yeah. Yeah, I see what you were doing with the original example now. Okay,
Because you have,
you
yeah,
yeah.
you have this n minus 3 plus 4. So what we're saying is n minus 3 plus 4 is n plus 1. We're trying to show n plus 1. So it's just
Mhm.
another way of showing n plus 1. If we're saying that this equation is true for n plus 1, where 4k plus 5l is, 4 cents times some number plus 5 cents times some number, then that 1 can be represented with n minus 3 plus 4. So we're adding 4 to both sides. And then that 4 can be factored, and because it can be factored, it fits neatly into this some number of 4-cent stamps plus some number of 5-cent stamps. And algebraically, that's what's going on over here. Okay, cool. I want to, I guess, erase some of this stuff. Is it okay that I erase this? Is everyone taking screenshots if they're, if they can, if they want to work with this? Okay, I'm going to go ahead and clear it. Okay, thank you, Suleiman. All right, let me get rid of these as well. All right, so now I want to move on to, where is it in our text? We've got some recurrence relations. We can do Fibonacci. Let's do the bit strings. There was a question that I saw on bit strings, which I think is interesting. So using recurrence relations to find the number of bit strings that without consecutive zeros. All right, so that was another one that was from the thing. So let's see. If we have bit strings without consecutive zeros of length 1, well, that means it's either going to be 0 or 1, and both of these are valid because neither of them contain 2 consecutive zeros, right? So if I have bit strings of length 2, I've got 0, 0, 0, 1, 1, 0, and 1, 1, right? So only 3 of these are valid because the first one here is what we're considering an invalid string, right? So if I want a bit string of length 5, how many of them are there that do not contain 0, 0 as part of the string? So to do this, we're going to do it recursively. And we're going to say, let me do another one over here. We're going to say that if we have some string that we know works, it's either going to end with a 0 or with a 1. So let's just copy that. 0 or with a 1. Or rather, you know what? Let me start with 1 and 0. So if it's n terms long, then, and we know that it's a valid bit string, then it's going to be whatever n minus 1 correct bit strings are for this one. That definitely ends in 1. And then over here, if it ends in 0, we know that it cannot end with 0, 0. That's not possible. So it's going to have to end with 1, 0, which means that it's going to be a correct bit string of length n minus 2. Right? So let's say we want all the 5 bits length, bit strings of length 5. Well, it's going to contain all the valid bit strings of length 4 plus all the valid bit strings of length 3. Does that make sense? Right? So really what we have is kind of a Fibonacci recurrence relation here, where we're going to say that we have, we can name this a sub n is equal to a sub n minus 1 plus a sub n minus 2. Right? And again, if I'm considering that this bit string is a valid bit string and it's 5 bits, it's going to either end in 1 or it's going to end in 1, 0, meaning that the remaining bits are going to be the correct bit strings of length 4 and the correct bit strings of length 3. Right? So this is our recurrence relation. A sub n equals a sub n minus 1 plus a sub n minus 2. Now, if we are trying to find the bit strings of length 5, then we know that a sub n, a sub 1 rather, we found that out earlier. There's 2 of them, right? It's either 0 or 1. A sub 2, we found that out also. There's 3 of them. Because 0, 0 is not valid, but 0, 1 is, 1, 0 is, and 1, 1 is. So now we can just kind of plug this in. We can say, all right, well, we've got a sub n is equal to a sub n minus 1 plus a sub n minus 2. So a sub 3 is going to be equal to the previous 2 terms, a sub n minus 2, a sub n minus 1, which is 3, plus a sub n minus 1. Or I think I got those backwards. But, so this term, a sub 3, is going to be equal to the results of the 2 previous terms, and that's going to be 5. Then a sub 4, a correct bit string of length 4, is going to be equal to the previous 2, which is 5 plus 3. And a bit string of length 5 is going to be equal to the results of the previous 2. That's 8 and 5. And that's going to be 13 correct bit strings. So does everyone see the logic as to how we've created this recurrence relation? Does anyone have any questions about how we came up with this? If not, then I'm going to move on. Maybe we can do, I think we have Fibonacci's, which is like related to this as well. Because, I mean, this is essentially the Fibonacci recurrence relation. There was one question that I saw in the sheet that had to do with finding an explicit formula for the Fibonacci numbers. So we can do that next. But I just want to make sure that everyone knows that, the logic of how this works. Okay. So Fibonacci's, we can just kind of, go on from here. I'll just move this off to the side for now. Fibonacci's have the same relation, right? So f sub n is equal to Fibonacci n minus 1 plus Fibonacci n minus 2. And that's the same relation that we just found. So the bit strings of that correct configuration was in the same, wheelhouse as Fibonacci's. So what we say for Fibonacci's is how we had a base case over here where a sub 1 is 2 and a sub 2 is 3 for the other problem. For Fibonacci's, we want to say f sub 0 is equal to 0 and f sub 1 is equal to 1. And we'll eventually be building the same series as all of that, right? It's going to all basically be the same thing, because 0 and 1 is 1, 1 and 1 is 2, and then from that point on it would all equal the same. But for us to create a way of going about this mathematically, we're going to have to work with this recurrence relation f sub n equals f sub n minus 1 plus f sub n minus 2. And to do that, we can make the assertion that f sub n is equal to r to the n. And then that means that f sub n minus 1 is equal to r to the n minus 1, and f sub n minus 2 is equal to r to the n minus 2, right? So now if we're going to use that in the equation and sub everything in, we're going to end up with f sub n, or actually r to the n. We're subbing everything now, so this f sub n equals to r to the n is going here, right? And then we're saying that is equal to, I can just copy this over, r to the n minus 1 plus, I'm going to copy this one over as well, r to the n minus 2. So now that we have this, there's a way that we can simplify it. The common term, the smallest term amongst all of them, is going to be n minus 2. So if we divide everything by n minus 2, we end up with r squared is equal to r plus 1. That's just dividing by common terms, which is r to the n minus 2. And that is going to equal r squared minus r minus 1 equals 0. So now we have a quadratic equation, right? So we started with our Fibonacci expression here at the top, right? And then from that, we were able to create a quadratic formula. And if we plug in using negative b plus or minus the square root of b squared, that whole thing, we end up with, let me see, over here. We've got r has 2 roots, is equal to 1 plus or minus the square root, I guess I'll just do this, square root of 5. All of that divided by 2, right? Is it easier to do it this way, or should I just try and use the pen? The pen just kind of, all right, I'll try and do it this way. I don't want to confuse you by using weird looking notation. So we have 1 plus or minus the square root of 5 over 2. And this is 2 roots because we have 1 plus the square root of 5 over 2 and 1 minus the square root of 5 over 2. And this, again, we just derived using the quadratic formula, which, again, is negative b plus or minus square root of b squared minus 4ac over 2a. It's funny because when I first took this class and that came up, it's like I hadn't seen that since 8th grade, but it comes back again. So we can put this out into 2 roots. We have r sub 1 is equal to 1 plus square root of 5 over 2. And the other one is going to be r2, their second root. Sometimes people use like Greek letters for this, but if it's easier to just call it r1 and r2, that's still just as valid. So I'm just going to do r1 and r2. So we have r2 is 1 minus square root of 5 over 2. And so far, so good, we have our 2 roots. Now, if we look back at our original equation, and we say that f sub n is equal to, well, now we have here, actually, let me just say, we have the generalized formula that we normally use, right? So let me just write that down first, because we're going to be referring to it. Generalized formula is f sub n is equal to some constant a times the first root that we just found is r sub 1 to the n, plus another constant b, and then this is times r2, the second root, also to the n. So now if we're going to go and plug in the ones that we know that f of 0 is 0, and f sub 1 is 1. So let's plug those in, and we're going to find that f sub 0 is equal to a times r sub 1 to the 0. Anything to the 0 is just going to be 1. So we can say that is equal to a plus b times root 2 to the 0. And again, root 2 to the 0 is 1, so we can just say a plus b. And we know that f sub 0 is 0, so we've got a plus b is equal to 0, and we can also say that means that they are inversely related. A is equal to negative b, and we can also say that b is equal to negative a. So I just list both of them because it may be more apparent to use one or the other. I mean, both are valid, but if you see one that makes more sense to use, then we can use that. So a is equal to negative b, or b is equal to negative a. So that's the case for f0 is equal to 0, right? So now we're going to do f1 is equal to 1. So we've got f1 over here. And we're saying that we're plugging that into 1 in this case is n, right? So f sub 1 is equal to a r1 to the 1, and anything to the 1 is itself, so I'm just going to say a times r1 plus, and then we have b r2 to the 1, and anything to the 1 is itself, so b r2. And we know that all of this, f1, equals 1. So really what we have is a r sub 1 plus b r sub 2 is equal to 1. So if we know that b can be expressed in terms of a, which we have over here, then we can express this entire thing in terms of a. I'm just going to move the 1 to the other side, and I'll say that 1 is equal to a r sub 1, right? Because that's just coming down. That's what we have up there. And b I'm going to replace with negative a. So instead of plus negative a, I'm just going to say minus a r sub 2. All right? I know it's a lot of steps, but so far, hopefully all of this is logically, making sense. So we've got 1 equals to a r sub 1 minus a r sub 2. So I can factor out a here, and then I can say that 1 is equal to a times r sub 1 minus r sub 2. So we got r sub 1 minus r sub 2. And all of that is equal to 1. Now, if we're looking at r sub 1 minus r sub 2, well, we know what those are. We've got that over here, and we got that over here. So let's try and simplify that. That's easy to do. So I'm going to take r sub 1 minus r sub 2, and let's figure out what that is. R sub 1, I'm just going to, instead of doing 1 plus root 5 over 2, I'm going to do this entire thing and say 1 over 2, just easier to see this way, 1 over 2 plus root 5 over 2. And that's the same. They share a denominator, so I can split them up this way. There's no problem there. And I'm going to say all of that minus, and then r2, you can see over here, is 1 over 2 minus root 5 over 2. Everything make sense so far? So if I have 1/2 minus 1/2, then these are going to cancel out. And if I have square root 5 over 2 minus negative square root 5 over 2, minus a negative is just plus, so I have 2 square root 5 over 2. You see how we did that, right? So root 5 over 2 minus negative root 5 over 2 is 2 root 5 over 2. The 2's cancel out. And I can say that square root 5 is equivalent to what this whole expression was, which was root 1 minus root 2. Right? So far, that's good. We've got root 1 minus root 2. So now we can plug that back into this equation, and we see that 1 equals a times root 1 minus root 2. And we can say that, let me just bring this over here. We say that 1 equals, okay, a times root 5. You see how we did that? We said r1 minus r2 is equal to root 5. And we have 1 equals a times r1 minus r2. So 1 equals a times root 5. And that means that a, if we can just divide out this root 5, a is equal to 1 over root 5, or the inverse of root 5. Right? So now we know what a equals to. And we're going to go back in our expression and say, here we have f sub n is equal to a r1 to the n plus b r2 to the n. We know that b is the inverse of a, so we're just going to rewrite this again. I'm going to draw a line, so now we're going back up here. I'm sorry, it's a lot of stuff to do, there's a lot of steps, but it all will work. So we have f sub n is equal to a r sub 1 to the n. And instead of doing plus b r sub 2 to the n, I'm just going to do, again, minus a r sub 2 to the n. And I can factor out a, and I can say that all of this is equivalent to a times r sub 1 to the n minus r sub 2 to the n. And then I can plug in the value for a that I got down here. The value for a is 1 over 5, so I can 1 over root 5. So I can say 1 over root 5 is equivalent to, and I know what r sub 1 is, right? R sub 1 is going to be 1 plus root 5 over 2. Right, so that's r sub 1. All of that to the n minus, and then now I have to do r sub 2. That's going to be 1 minus root 5 over 2. And again, those values are what I got over here and over here, right? So those are being plugged in. And that is also to the n. And that is our closed form for Fibonacci. The way that you would use this in practice is like saying, if I want to find the 10th Fibonacci, instead of finding the 0th and the first as the base case, then finding the second, then finding the third, then finding the fourth, going all the way up to 10, I could just plug 10 in here. I'd say that's 1 over root 5 times the 10th power of 1 plus root 5 over 2 minus the 10th power of 1 minus root 5 over 2. And that would equal the same number as finding it going in order of 0 to the first, and there's a second term, and then the first and second term is the third term, and the second and third is the fourth, right? So this is called a closed form. This means I can just plug in the value of n, and I'll get out the answer immediately without having to do any of the recursion. All right? I know there was a lot of steps there. I know it can be confusing. So I want to just, I want to just ask if anyone has any questions on how we approached that. Yes, we just use the formula and plug it in. It actually, I know it's a lot of steps, but at no point is it kind of like pulling anything out that we don't already have. We have all the resources here, we just have to rearrange them in a way that makes sense. So I guess I just want to say, when you have some function like f of n equals f of n minus 1 plus f of n minus 2, that's a linear homogeneous expression, right? In this case, we're able to, in any case that you're going to be asked, you're able to convert that into what we saw here, which is r to the n equals r to the n minus 1 plus r to the n minus 2. As long as you can simplify that down and use quadratics to find what the roots are, it really is just plugging in those roots until you find something that leads to a complete expression. So yes, you're absolutely right. It's you use the formula and then you plug in the values. With anything with algebraic methods like this, in algebra, you just want to make sure that you're doing all of the steps in being very careful not to, square something when you meant to, use the, r to the 1, you used r to the 2 instead or something like that. So the mistakes that can come in notation can lead you to the wrong answer. You just want to, just take it slow. Everything is there. You're going to follow a step by step until you get, to the answer that you're looking for. So yeah. I think there's another one that uses, it was a linear homogeneous recurrence relation that has a sub 0 is 2 and a sub 1 is 7. So I think we can do that one next as well. And we may have just enough time to finish that before a little break and then continue on with some other stuff. Oh, okay, so I see a question here. How did I get r equals 1 plus square root 5? So that should be square root 5 over 2. This here, the way that we got that was from, would it be okay if I made some space by deleting some of this? Or, yeah, okay. So I'm just going to delete a few things. I'll leave the answer up there for now. So let's... All right, so you want to know how we ended up with this one to begin with, right? So let me just take this. We had r squared is equal to r plus 1, right? And the way that we got that was because originally we had this, r to the n, right? We had f to the n, so we replaced that with r to the n. Then we had f sub n minus 1, is r to the n minus 1. And f sub n minus 2 is r to the n minus 2, right? So we can say, I'll just write it out instead of typing it. So let me just, I want to be absolutely crystal clear because it's really important that we get this step down. So we've got r to the n is equal to r to the n minus 1 plus r to the n minus 2. And again, that is just, we used the assumption that f sub n is equal to r to the n. And that is kind of arbitrary that we did that, but it works because we're consistent with it, right? If we're saying that f sub n is equal to r to the n, then we're also saying that f sub n minus 1 is equal to r to the n minus 1, and f sub n minus 2 is equal to r sub n minus 2, right? So as long as we're consistent with it, then we have a valid expression. Now, what I said to break down to get to this term over here, right? I said we have to divide by the common term, and the common term is the smallest term. And if I divide all of this by r to the n minus 2, to the n minus 2, and I know this is not done so commonly, so it might take a little convincing, but let's just sub in n so that we can figure out what this really means. If I say n is 10, then what I'm really saying on this side over here is r to the 10 divided by r to the 8, right? And that's going to give me r squared. Or I could say r to the 30 divided by r to the 28, and that's still going to give me r squared. It doesn't matter what n is, it's always going to equal n squared once I simplify. So that means that I have r squared is equal to, I can do the same thing for this side over here. If I have 10 minus 1 is 9, and I divide that by 10 minus 2 is 8, then r to the 9 divided by r to the 8 is just going to be r. And that's true for any n, right? And I have this, and these are the same terms. So r to the n minus 2 over r to the n minus 2 is always just going to be 1, right? So you're dividing it by itself, so it's going to be 1. So now that I have this, I'm going to subtract both sides. I'm going to subtract the r and the 1 from the right side, and I have r squared minus r. minus 1 equals 0, right? So if I subtract this r and I bring it over here, and I subtract this 1 and I bring it over here, I'm going to equal 0. So now this is a quadratic expression, and that means that a, the coefficient a, is equal to 1. The coefficient b is equal to negative 1. And the coefficient c is also equal to negative 1. Right? So that's over here. A is over here. Right? And I could say plus br plus c. Right? That's another way of looking at it. But a is 1, b is negative 1, c is negative 1. So if I know all of that, then I can say negative b plus or minus the square root, this is the quadratic equation, right, of b squared minus 4ac over, all of that over 2a, all right? So if b is negative 1, then negative b is just going to be 1, plus or minus. Now I have the square root of b squared, so negative 1 squared is just going to be 1, minus 4, a is 1, c is negative 1. So negative 4 times, what is it? It's just going to be, negative 4 times negative 1 is just positive 4. All of that over 2 times 1, which is just 2. So this 1 plus 4, we can just call this 5. So that's going to be 1 plus or minus the square root of 5 over 2. And we're looking for the roots, right? So the roots are going to equal 1 plus or minus the square root of 5 over 2. So the first root is 1 plus square root of 5 over 2. And the second root is 1 minus square root of 5 over 2. So that's how we got those roots. Okay, we did counting bit strings. Okay, generalized pigeonhole principle. I think that one we can do in the next 5 or 10 minutes. So that should be not so bad. So let me just, I'm going to clear out all of this stuff. Pigeonhole has to do with, Suleiman, is there an easier way of clearing this instead of running back and forth? I've never figured it out.
If you're using the zoom drawing, then I think there's an option to clear all drawings.
Oh, okay, the garbage can. All right, cool.
Yes.
Nice. All right. So, thank you. So, generalized pigeonhole principle. This is including the corollary, including the formula, the card problem. Okay. So the way that pigeonholes generally work, and let me just delete these two now. Pigeonhole is like saying, I've never seen a pigeon burrow in a hole, but this is always the example that they use. But just think that you have objects in boxes, right? Or you can say like a ball going in a box. So if I have, let's say, 5 green balls and I have 4 boxes, the way that you see it in the textbook is they call it pigeonholing, and they're going to say that these are 5 pigeons and 4 holes. But if you can't remember that, just think you have objects going into boxes. If I have 5 balls going into 4 boxes, this ball can go in this box, this ball can go in this box, and so on and so forth. But by the time I've filled each box with a ball, this ball here that hasn't been put into a box yet, it must go into a box that already has a ball. It doesn't matter which one. If it goes into this one, A, B, C, or D, it doesn't matter. It's guaranteed that at least one of these boxes is going to have more than one ball in it. And we can calculate, how many at least. So there's something that you've seen in your textbook. It's called the ceiling. And I think they use n over k. Just know that n in this case is the objects. In this case, it's 5. And 4 is the thing that you're sorting it into, which is boxes. So if we're saying it's the ceiling of n over k, That's equivalent in this case to the ceiling of 5 over 4. And if you're unfamiliar with ceiling, what that means is it's saying round up. It doesn't matter how small the decimal is. If there's a decimal point, it's going to round up to the next one. So in this case, 5/4 is 2.25, right? And because there's any bit of decimal point, value after the decimal point, then this is going to round up. No, it's 1.25, I'm sorry. 1.25. This is going to round up to 2. So 2 balls are going to share 1 box. Right, there's going to be, in that case. So if we, let me see, there were other examples that I think also make it, pretty clear. I'm going to look at pigeonholes. Sorting n over k. Yeah, so when we're doing this with cards, we have 4 suits, and in a standard deck of 52 cards, there are 4 suits. So if I want to say how many cards do I need to guarantee that I'm going to find, what was it, 3 cards of one suit? I think that was the question, right? So I can choose a heart for my first card, and I can choose a heart for my second card. Now, it's not guaranteed that the third card is gonna give us a group of 3 of the same. I could do a club, right? If I have a club, I have a heart club, and let's say I do another club, right? So I have 4 cards, and then I can say I have a diamond, and I have another diamond, so that's 6 cards so far, and then a spade, right? And another spade. At this point, I have 8 cards, and it doesn't matter what card comes next. It's guaranteed that at least, one of these suits is going to have a group of 3. So let's say I have a heart again. So when I get to 9 cards, it's guaranteed that I'm going to have, right? So if I do this and I take n over k, I've got 4 suits to choose from. Think of those like the boxes. And I'm choosing from 9 cards, 9 over 4, that's going to give me 2.25. And the ceiling means that because there's a decimal value, I'm going to go up to 3. And that means I have 3 cards of the same suit. That's going to be these 3. All right? Got a heart here, and a heart here, and a heart here. So it requires 9 cards to guarantee, absolutely guarantee, that I'll find 3 of a kind. All right, so it is 1 o'clock. Suleiman, do you think we take a 5-minute break and then continue?
Yep, sounds good with me. We'll take a quick break, let people get a drink of water or whatever they need, and we'll continue in 105.
Great. All right, sounds good.
Alrighty, so let's okay. Here's a textbook and I have a blank PDF open. For those in the chat, what is the next topic do you want to work on? We have big O concept, we got big O notation. If you want to do a bit of more recurrence, we got towers of Hanoi, solving recurrence relations, and maybe a bit of truth tables. What the hell is following me? I don't know. What do you guys want to do? We'll work on whatever you guys want. Let me see if I can find the big O notation section while you all decide. Leave it. No. Right there. No. Growth of functions. Yes, sorry. So everyone there? Any vitals? Everyone okay? Anyone here? Um, if there's no, can we do a big notation? Sure. Okay, let's do a big notation. I was planning on doing that first. All right. So does everyone here like have a basic understanding of what big O notation is, or um, would you like a quick explanation of that? Let's do a quick explanation. So in CS220, you're going to learn something about big O notation, and you might be wondering why is it important? So we have functions, right? Say this is a function. Let's do a different color. Tab right here, different color. So this is our function. It's not drawing, right? We want, and there's a notion in computer science and mathematics called big O notation, which is we want to bound the function, right? So in this case, we want to say that this function doesn't grow farther than the red function. So green doesn't go farther than red. So let's say this is e of x, and the green is f of x, right? Think of it as like an upper bound, right? So let's give a nice comparison. I'm planning for a party, right? You know when you plan for like big events and you want to try and estimate who's going to come up, you have three options. I think big omega, you got theta. Correct me if I'm wrong. I'm not. There's what is it? There's a big O notation. There's omega. You'll see a couple of these in 220 theta, and there's a little o, right? Um, think of big O as like an overestimate, right? It's just like an overestimate, right? We are inviting like a lot of people to the party. We don't know how many, but I want to be safe. I don't want to look like I don't want to embarrass myself and accidentally order less food than people show up. This is an overestimate. I'm not sure which one of these, but one of these two, either big omega or big theta, it's like an underestimate. So it's like a lower bound, right? So like overestimate, I'm predicting maybe 1,000 people max is going to show up. It's not going to go above 1,000 people. And us underestimate is like I'm saying at least 500 people are going to show up. And little o, you'll see is like a pretty like almost exact estimate, right? So like I'm not sure, but around 750 people will show up. Out of all of these, big O is usually the best because you'd rather overestimate than underestimate, right? Think about it like this, especially as computer scientists. When we create algorithms, we don't want to underestimate how much it's going to take, especially for like algorithms that have to do with important tasks. So we always want to have an overestimate of what's going to take. So that's where big O comes in, right? So now let's get to the actual concept itself. We always want to bound a function. So here we have f as a function. The idea of big O is we want to find the function g that from some starting point, let's call this starting point x0, you might see other notations of it, but g is, or let's actually say some constant times g is always going to be greater than or equal to f from for all x greater than or equal to x0. This is basically saying from x0 onwards, so from this range, some constant times g of x is always going to be greater than or equal to f of x. Is everyone okay with that notion? Is that any questions about it? Because that's inherently the big that's the big idea behind big O notation. We want to bound f by some function g. Well, some constant c times g could be one, but we want to bound f by g. Let's give an example real quick. So say I want to find the big O of this function x squared, say 3x squared plus 4x plus 2, right? I want to bound this function. Um, so what I want to do, this is a technique I learned in 313 or 220, either one. I like taking each term individually, and then I see what's greater. So I know that 3x squared is greater than or equal to 3x squared. If you hear yelling in the background, my brothers are playing video games, and I don't know why they get so loud. I mean, to be fair, I play loud too. So for x zero, I'm sorry, for all x greater than or equal to 1. Before I continue, does anyone have any questions about any of this so far? What I've explained? This is just like a little bit of a background I wanted to give. Any questions? Any questions? I'll wait a quick second for people who have questions in the chat, or if you have no questions, you say no questions. Is everything okay? The people who are in chat? All good? All good? Waiting for one more good, then I'll move on. There you go. Okay. So 3x squared is greater than or equal to 3x squared for all x greater than or equal to 1. Great. 4x, let's actually do this. We want to find something greater than or equal to 4x. 4x. So I'm going to say x squared is greater than or equal to 4x for all x greater than or equal to 4. Right? Because once I hit 4, 4 times 4 is 16, and 4 squared is 16. So once I hit 5, 4 times 5 is 20, 5 squared is 25. We're good. And now I'm going to say 2 is going to be less than or equal to x squared. And I'm going to say for all x greater than or equal to 3. Or actually, I can say 2 even. It's a line is bound. 2. Because 2 squared is 4. 4 is greater than or equal to 2. Okay? So now, what do? I'm going to add up these terms. I'm going to get, because remember, we have this little rule right here. If A is greater than or equal to B, and C is greater than or equal to D, then A plus C will be greater than or equal to B plus D. We could add them. So I'm going to add them all together. 3x squared plus x squared plus x squared. What is that going to give me? So I want to check quick. What am I going to get? 5x squared. Bingo. So 5x squared is greater than or equal to, if I add the right side, I get 3x squared plus 4x plus 2. And from the right of from these portions, I'm going to take the greatest one because I want to take the highest of these px zeros. If I choose something that's not, then I could like be um disproving what I already proved. So I'm going to choose the greatest, which is 4. And we're going to say for all x, let me write for all as well. For all x greater than or equal to 4. So what do we see? We now have 5x squared. This is our f of x. So our g of x is going to be x squared. And our c is going to be 5. And our x0 is going to be, I'm sorry, I'm pointing the wrong thing. X0 will be 4. Okay. So now we just proved that this function, f of x, is big O of x squared. So let me write this right here. Let me write this right here. F of x. F of x is big O of x squared, where c is equal to 5 and x0 is 4. Any questions? Any questions? Any questions about this? Any questions? Nope, nope, no questions. So that's one. So that's what you see here. So we want to bound it, c times g of x, wherever x is greater than k, right? Big O. Um, that's so once again, see how we proved it here? I use a similar notion, right? So I see each individual term, compare it. You get this. You could, okay, let me write this as well. Um, mm, how do I word this? Big O's are useful, but if the function you're finding big O of is too high of a bound, it loses its use. So for example, I could say, let's say this is x squared. I could say that x squared is less than or equal to x to the 100th for all x greater than or equal to 1. This is technically right. This is a big O. This is right. X squared is big O of x to the 100 for c is equal to 1, x0 is equal to 1. But this isn't useful. This is like if I drew it out here, this is x squared, and x to 100 is somewhere way up there. It's a bound, but it's most likely not going to help me. Like I could technically say I'm overestimating who's going to come to the event and order 10,000 meals. But if it's very unlikely, unless it's a very big event, that 10,000 people show up in the first place. So even though this is correct, this isn't useful. Like we don't want to say the tighter we could get to like x squared is better. Like here, right here, this is better. That's why we have the constant c is 5 and x0 is 4. It allows to get closer to the original function. Because once again, this is technically right. I could say this is x to 100 and I will be right. But that in terms of like CS and like actually trying to analyze the function, it makes no help to us whatsoever. So I just wanted to bring that up. And you see here how we try to get a lower C, a lower C, but with a slightly higher starting point. Okay. So right here, we see like you see a visual representation of it as well. We see this is the original function, the blue right here, and x squared is here, but constant 4 times x squared is gonna be upper bound. Okay. Big O notation. I think that's good. Once again, another here. Okay. Here's another example. I want to prove that 7x squared is big O of x cubed. This one's a bit more obvious because the exponent is different. So you could just say right here, um, 7x squared is less than or equal to x cubed for all x greater than or equal to 7, because 7x squared is 7 times 7 times 7, and 7 cubed is 7 times 7 times 7. So here's another example of it. What I do want to show is another example of right here. So here's something that you could get on your exam, proving that something is not big O of another term. Before I move on, are there any questions so far? Any questions about big O notation from what we went over? No question. All right, I'm gonna take the silence as no question. So I want to prove that n squared is not big O of n. So let's do that up here in top corner. So here is one example where we want to use how to prove big O and try to disprove it. So you're gonna see the notion of proof by contradiction, right? And the idea is you want to assume something is right, then get to something that is incorrect. So let's see an example here. And it's kind of like hitting two birds with one stone because we want to prove proof by contradiction. So I want to prove that n squared is not big O of n, not big O of n. So let's assume it is. So assume that means if n squared is big O of n, that means n squared is less than or equal to n some constant times n for all x greater than or equal to some x0. Okay? But okay, what I want to do is if there are no questions on this. Yes, please. From past review sessions, I usually take silence as like move on, but if you don't have any questions, that would be very helpful so I don't like waste time just blankly staring at your profile pictures. Um, Anywho, so I want to prove that this isn't the case. Well, what I could do is I could divide both sides by n. That's an n, by the way, by n. And what the hell is that? H or an n? N. And what do I get? N squared divided by n is less than or equal to a constant. Is this true? Someone in the chat, is this true? Remember, n's a function and c's a constant. Is n always less than or equal to c? Someone in the chat answer that, please. Getting user participation. No. Why is that? Someone answer to me. Why is it the case that n is never less than or equal to c? Why is that nonsense? Anyone? Anyone at all? Why is n less than or equal to c? Nonsense. Why is it not right? Y'all are thinking no, but I want to see why it is. Why is it incorrect? I gotta make sure y'all are paying attention. All right, what is n in this case? What is n? Can y'all hear me? Am I not going through? Is it not not being heard? Uh-huh. N's a function, right? So n's a function. So n is like think of it as like a linear function. So f of n, that's a horrible line. Right? F of n is equal to whatever n is, right? So that's x, right? For example, so n. So it looks like this, right? And that's a function. What's c? C is a constant, right? This is a constant. But remember, if n is a function, so it's always increasing or changing, and in this case it's increasing because the slope is positive, will it ever be bound by a constant? No, because regardless of whatever constant I choose, n will always go above it. Does that make sense? So that's why this is a contradiction. I don't know how to do the little things. How to do the little two swords. Oop, oop. Contradiction. So what we initially assumed, this n squared is big O of n, is wrong. So it has to be the case that n squared is not big O of n. And you see the proof right here. Any questions about that? Any questions? Everyone okay with that notion? We'll do one more proof by contradiction, but okay. So we want to show that we know this. We want to show that this is not true. So once again, let's assume it is. So this means that x cubed is less than or equal to 7x squared times some constant for all x greater than or equal to some x0. Okay? Same thing. I'm going to divide both sides by x squared. Divide by x squared. I get x is less than or equal to 7 times a constant for all x greater than or equal to x0. Is this true? Remember, 7 and c and constant are constants. X is a function. Is that what I just wrote? X. Yes, it's not true. Yep, it's also a proof by contradiction. Why? Because we assume that it is right. We assume that this is true, and we get this. But this isn't true. X is not less than or equal to 7 times a constant. X is a function. X can keep growing. 7 times a constant is a constant. That stays in one specific point. So that means this is a contradiction. And then this, what we initially assumed, is then incorrect. Any questions about that? Any? All right, no questions. Let's move on. And I think there's a graph here for a useful like big O. Right here. So this is like another useful thing. So if I have a function of a polynomial, usually it's the case that the highest exponent is a big O. So once again, we could prove it using the big O notation, but this is like a neat rule to have. So let's scroll down. Usually have a graph here of some sorts. Right here. So this is what I wanted to show. So it's neat to have this type of graph because I'm not sure how Delaram or Alla do their exams, but when I had Mitchell for 220, he gave me some sort of ordering questions. Like here are some functions. Order them in terms of which one's bigger than the rest. And it's nice to memorize this. So always constants are fastest, logs are then second, then you have degree one, n log n, and you have polynomials. There's all sorts of polynomials in here. And you have exponentials and factorials always grow largest. Okay, that's it. You might also need master theorem. Is there a master theorem? Right here. Also neat ones to have. So if I have two functions, the sum using trilateral inequality, right? We got this. This is another one you want to think right here. Okay, here. F1 of x is big O of g of 1 of x, and F2 of x is big O of g2 of x. Then their F1 plus F2 is big O of g of x, where g of x is the max, right? Pretty straightforward, right? Because if I take the maximum of the two g of x's, it should be a bound of adding both of them. Once again, if I think f1 of x is x squared, this is u of x squared. Hey, this is x cubed. This is x cubed. Then if I add x squared plus x cubed, once again, that's going to be big O of x cubed because it's the highest exponent. Okay? Similar thing here. If they both have the same g of x, well, if both functions are big O of the same function, then their sum is also big O of the function. Also, before you guys leave, Joe, could you put the feedback form in the chat in case anyone needs to leave early? It's a nice way
Yeah.
to get
Yeah, sure.
feedback.
Let me go grab that now.
Thank you. If we have a product instead, then the same thing. It's going to be a product. So this is a bit more straightforward. Okay, I don't think you're going to get big omega and big theta. These aren't as popular. They're still, you still learn them, but they're not used as much. So I don't think you're going to get them on the exam. Big omega is just, uh, yeah, yeah, this is the opposite of big O, right? And then you have big big theta. Yeah, big theta. I was wrong. Big theta is if you have big omega and big O. So if a function is big O of another function, and so if function one is big O another function, and function two is big O of that first function, then they're both big omega. So this is what I think was here. So this is not little o. This is big theta. Almost exact. Almost exact. Right? Big omega is an underestimate. Big O is an overestimate. Big theta is like almost on target. Okay? You'll most likely see big O used a lot more than anything else, but it's still neat to know the other two. All right. Any questions? Any questions? Is there another topic that anyone wants to go over next? We got a couple of choices. Let me see what the other ones are. Uh, we got truth tables, Tower of Hanoi, some more recurrence relations. We could possibly do another proof by induction. The feedback form does not have this 220 session as an option, or actually no 220 option. God damn it. I will let Mike know. Give me 1 second. Strong induction. Okay. Give me 1 second.
For the feedback form, should we do Steinberg February 27th again?
Yeah, I think, yeah. Feel free to do Steinberg February 27th, and then we'll change it on the back end as well. Okay, so strong induction. Let me try this section for it. Induction, strong induction. Okay, so have you all heard of weak induction? So you just heard of induction. Okay, let me give a bit of a background. Sorry, Max just telling me he can't fix the form. So for anyone filling out the feedback form, put 212 Steinberg and we'll change it on our back end. Okay, so the example Joe did at the beginning, that's an example of strong induction. Let me actually pull up another blank page. Let's tab. There you go. Okay, so here's how I like to think of induction. Got an infinite ladder, right? Ladder to heaven per se, right? And this keeps going on. And got the little sun here, smiling. This is me, still on the first rung. This is Joe at the top here, right? Okay, so whenever we want to prove things, it's easy to prove if there's a limited number of cases, but if there's an infinite number of cases, we can't prove it just by testing it out. All right, for example, if I want to prove a function for all, can we do a recurrence for all numbers? Sure. If I want to prove a number, a question for all n and say the natural numbers, then I can't just plug in every natural number because first of all, this is infinite, and I can't really test it out for every single one. So this is where we have induction. Okay. So the idea of weak induction versus strong induction. I like to think of it as like, well, my professor who taught me this thought of it as weak induction is usually good enough for like formulas, but whenever you have like to prove something with multiple base cases, that's strong induction. Let me show you an example. Induction is always this format. Can I first get on the ladder? This is the base case, right? I want to get up the ladder all the way up. We can't prove I can get to each rung, but I can prove it like this. First, we want to get on the ladder itself. That's the base case. Once I'm on the ladder, the inductive step is given I'm on any rung. So I'm on rung K. If I can go from rung K to K plus 1, then we're good, right? Because that's all I need. All I need to prove is first I could get on the ladder, and then from this I could go from any rung to the next one, and I keep repeating that to the next one, to the next one, to the next one, all the way up. If I can keep going to the next rung, I can go all the way to the top of the ladder, to the top of the ladder. Okay? The difference between weak induction versus strong induction is this. Weak induction says if I'm on any rung K, I can go to the next one. And in a lot of cases, such as when I have to prove summations, I'll do an example right now, weak induction is enough. Strong induction says this. Given that I was on any rung from some starting point, let's say K0, right? So K0 is the base case. Up until K, all of this proves that I can go to the next one, right? So why is there a distinct difference here? Because weak induction is saying any, if I'm on any step, I can go to the next one. Strong induction is saying given I was on any past step, I can go to the next one. Why is this important? Okay, let's go back to the example we started off with. I want to prove that any number greater than or equal to 12 can be made up of some combination of fours, let's say 4 times A, and some combination of 5 times B. Well, if I can just prove like this, let's see like this. There is a way to do it with weak induction. It's very complicated though, but let me just show you why. I'm going to prove the base case. We know that 12 is equal to 4 times 3. Bingo. Okay, so now I want to say n is equal to 4 times A plus 5 times B. I want to prove n plus 1 is equal to 4 times A plus 5 times B. Can I use this formula to get this formula? I can't really add 1 on both sides. Right, I get this. I get n plus 1 is equal to 4A plus 5B plus 1. But that's not, I want this. This doesn't really help me. So in order to solve this, we do what we did before. We have more base cases. So we go from 12, 15, and then we can use a notion that not just n is equal to 4A plus 5B, but everything before it too. So for all n greater than or equal to 15, n minus 3 is equal to 4A. I'm sorry. For all n greater than or equal to 15, n is equal to 4A plus 5B, right? So then I can choose n minus 3, right? See how the difference is? N minus 3 is equal to 4A plus 5B. I won't go through the rest because Joe already did. And we saw the proof. We could add 4 on both sides, yada, yada, yada. Here, we're not just using the last step. We're using a step 3 steps before. We're not even, yeah, we're using like way before it. This is strong induction. Weak induction is what we had here. And we can't use weak induction as simply to prove this. Strong induction is much easier. However, in a lot of cases, weak induction is enough. For example, I want to prove the sum from I equals 1 to n for all I is equal to n times n plus 1 over 2. Okay? Well, what we could do is I could say, assume that for some k less than or equal to n, at the sum from I equals 1 to k of I is equal to k times k plus 1 over 2. Uh, so I want to prove k plus 1. I'm sorry, that's k plus 1. The sum I want to prove that the sum from I equals 1 to k plus 1 of I is equal to k plus 1 times k plus 2 over 2. Well, what I could use, I know the sum from I equals 1 to k plus 1, that's the sum from I equals 1 to k of I plus k plus 1. What do I know? This portion right here, I'm sorry, delete this. This portion right here, we already assumed is this. So that's k times k plus 1 over 2 plus k plus 1. Okay. I'm going to then do simple arithmetic. I'm going to say this is going to be 2 times k plus 1 over 2. So it's going to be k times k plus 1 plus 2 times k plus 1 over 2. Factor out the k plus 1, I get k plus 1 plus 1 times k plus 2 over 2. Well, that's what we wanted to prove. There we go. So here's an example where weak induction is enough. So that's the difference between weak induction and strong induction. Any questions? I yapped it for a bit. Is there any question about this? Any? You'll usually see one of both. If you see that if you can prove something using just the last case, then you're good. If you need more than just the last case, then you need strong induction. Right? Okay. So any other questions about induction? We're going to move on to recurrence relations and right now then. That's the case. Okay, if that's the case. Let's move on to recurrence. Hmm. Okay. So let's do an example. In general, most of the recurrence cases follow one of two. Like here's a degree 2 case. C1, C2, suppose that R1, yada, yada, yada. And the sequence A of n is a solution to this recurrence relation. A is equal to C1 times this. A minus 1, yada, yada, yada. If and only if. Okay, let's do an example here. Hopefully they have an example. Right. So I think this is the one Delaram gave in her review. So we want to solve the solution of the recurrence relation. A sub n is equal to A sub n minus 1 plus 2 times A sub n minus 2. with A0 is equal to 2 and A1 is 7. Okay, we could use this theorem right here and do the following. The characteristic equation is going to be r squared minus r minus 2. How do we get that? Remember, we have the characteristic equation. C1, C2. What are C1 and C2? I'm sorry, where are we? Right here. C1 is 1, C2 is 2. So the characteristic equation is going to be r squared minus 1 times r minus 2. Let's right here follow it. Yep, r squared minus C1 is 1, C2 is 2. Bingo. Okay, so let me just write this here. So C1 is 1, C2 is 2. All right, what are the roots of this equation? Well, we could factor it. We get r squared minus r minus 2 is 0. What two numbers multiply to minus 2 and add to minus 1? That's r plus 2. I'm sorry, r minus 2 minus 2, r plus 1 is 0. So r is equal to 2 and minus 1. And what do we get? We get this. A of n is equal to alpha 1 times 2 to the n plus alpha 2 times minus 1 to the n. And we want to solve. Well, how do we solve for alpha 1 and alpha 2? We use the constants given. A0 is 2, A1 is 7. If A0, right, so A sub 0, let me write the previous step. A0 is equal to alpha 1 times 2 to the 0 plus alpha 2 times minus 1 to the 0. Okay, what does that mean? 2 to the 0 is 1, minus 1 to the 0 is 1. So we get this equation. And then, what do we get? Alpha 1 is equal to alpha 1 times 2 to the 1 plus alpha 2 times minus 1 to the 1. What do we get? This is going to be A1. I'm sorry, this is 7. This is 2. This is 7. So what do we get? We get 2 is alpha 1 plus alpha 2. And 7 is 2 alpha 1 minus alpha 2. System of linear equations. Let me add them first. Combine these, I get 9 is equal to 3 alpha 1, which means alpha 1 is 3. And if alpha 1 is 3, that means 2 is equal to 3 plus alpha 2. Alpha 2 is equal to minus 1. And this is our final equation. Any questions about that? That was case 1. I won't go over the Fibonacci sequence again because Joe did a good job of it. No questions? Good, good, good. Very nice. All right, so let me see if there's another case of this. Once again, this is the one that Joe went over. All right, so here's the second case. If it's only one root, then if there's only one root to the equation, then we have this. This is the equation I'm going to use, right? We have an extra n here. So most of it's the same. Let's do this example here. I have a of n is equal to 6an minus 1 minus 9. So this is going to be c1, c2. So it's going to be the right here. And what is this? R squared minus 6r plus 9 if 0. If you factor it, you get r minus 3 squared. So our only root is r is 3. And thus the solution is going to be alpha 1 3 to the n plus alpha 2 n 3 to the n. And then once again, here is we plug and chug. We use the constants here, these conditions. So we know that a0, which is 1, is equal to alpha 1 times 3 to the 0 plus alpha 2 times 0 times 3 to the 0. This becomes 0. This is 1. So we know alpha 1 is 1. Pretty easy. A2, which is 6, is equal to alpha 1 times 3 to the first plus alpha 2 times 1 times 3 to the first. Well, alpha 1 is 1 times 3 to the first plus alpha 2 times 3, which is 6. What do I get? I get 6 is equal to 3 plus 3 alpha 2. I did do something wrong? I don't think I did. I didn't. Okay. Minus 3 minus 3. 3 is equal to 3 alpha 2. Alpha 2 is equal to 1. And thus we get this equation. Okay. And that's the second case. I don't think you're going to have to worry about the general case, but this is a more general case. If we elongate it, we get the roots, we get the approximation, and then boom. Any questions? Those are the two cases you're most likely going to have to deal with, though. Case 1 and case 2. Any questions? I went through that a bit fast, so if you have any questions, feel free to let me know. Yep. The main idea, you find the roots, bingo. If you find if the roots are two distinct roots, you use this equation and then you solve. If it's only one root, you use this equation and you solve. Okay? So that's how it works. You use the constants, step one, find the constants near next to it. So constant, constant. You plug that into the characteristic equation. There's the characteristic equation right here. And depending on the number of roots, you either use this equation for two distinct roots and this equation for one root, and then you solve for alpha 1 and alpha 2. Any questions?
I'm actually not sure. Suleiman, do you know where this recording is going to be? Or would you two know?
If there are no questions, I could show it right now. Before we show it, are there any last questions? Any last questions? I mean, while I pull it out. Mm, mhm. And then that's in the way. All right. So if you go under the QC Learning Commons website, once again, CSCI resources right here, and you'll see CS220, bingo, right? So this is the review, and we're going to have it here. Does that answer your question? When will it be uploaded? It's a Saturday, so uh I'm not gonna force Ming to upload it right now. Um I want to say when's your exam? When does it it says it over here. 216, 3. Oh shoot. It should be uploaded before the Delaram's exam. Before Alla's exam, I'm not entirely sure. But we'll try to get it out by Monday. We'll try. No promises though. If you're in Delaram section, it should be out but there before your exam ideally because it's a bit later. But um what was I saying? If you're in Delaram's section, the exam's a bit later. So yeah, it should be there before the 24th, but um we'll try for Monday.
Hey guys, also just remember to fill out the feedback form before you leave, and I'm gonna copy it and post it again over here. Just also keep in mind there's no option for selecting 220, so we're using Steinberg's 212 on February 27th, so you can just select that one, and later on we'll correct that. We'll go into that file and move everything over.
Right? Sounds good. Thank you all for attending the session. I think we ended 2 minutes early too, so that's nice. I will stop the recording.